Hi, in today's video I would like to introduce a very nice improper integral. It's set as x goes from 0 to plus infinity, sine of x squared dx. In fact, this is very important and useful integral. So there is a bunch of ways you can solve this integral. You may use the Cauchy theorem for the closed contour in coordinate complex numbers, but I'm not going to do that. I'm going to use a nice technique. Okay, let's get started now. For the Euler formula, we have the e to the ix squared equal to cosine x squared plus I sine of x squared. So this integral, as x goes from 0 to plus infinity, of sine of x squared dx equal to imaginary of integral as x goes from 0 to plus infinity of e to the ix squared dx. Okay, I'm going to do the substitution in order to transfer this I number complex into regular integral. Okay, so let's set e to the x squared equal to minus z squared. Okay, minus 1 equal to I squared z squared. One of the I will be cancelled out. I will get x squared equal to I z squared. Okay, by taking the square root on both sides, I will get x equals square root of I plus or minus square root of I is multiplied by z. But since we are talking about the positive numbers, because x goes from 0 to plus infinity, we don't need the minus sign, so this one become plus. I'm going to take the differentiation of this one. I will get dx equal to square root of I dz. Okay, so I'm going to plug this information into this integral. I will get I integral as x goes from 0 to plus infinity of sine of x squared dx equal to the imaginary of this integral as x goes from 0 to plus infinity. I already replaced ix squared with minus z squared dx. It was square root of I dz. I'm going to take this square root of I outside of this integral because it's considered as a constant. I will get imaginary number of this number is multiplied by this integral as x goes from 0 to plus infinity of e minus z squared dz. Okay, I'm going to evaluate two things separately. I'm going to evaluate square root of I as a number complex. I'm going to evaluate this integral as a Gaussian integral. Okay, by using Jacobian matrix. So first table, I'm going to evaluate square root of I. Square root of I equal to a plus ib. I'm going to raise number 2 as a power on both sides. I will get I equal to a plus 2 times ab is multiplied by I minus b squared. By doing I squared equal to minus 1, I will have an equation system here. By matching the numbers, real number with a real number, real number with a real number, imaginary number with the imaginary number. So I will get I equal to 2 times ab, which is 1, equal to ab. I will get also as a real number a square minus b square equal to 0. Okay, so I'm going to solve this equation. Here I will get a equal to 1 divided by 2b. Here I will get a square equal to b square. I'm going to replace one of these equations into the other. So this equation, I will get a square equal to 1 over 4 b square. Second equation, I have a square equal to b square. Equivalent, I'm going to replace b square with its value. I will get a square equal to 1 over 4a square. By multiplying both sides, by multiplying side by side, I will get 4 times a to the fourth equal to 1. That's mean equivalent a to the fourth equal to 1 over 4. It's equivalent a equal to plus or minus 1 over 4 to the 1 over 4 to 1 over 4. Okay, equal to plus or minus 1 over 2 to the 2, and also here I will get 1 over 2. The whole thing is 1. I'm going to simplify this exponent on this form. I will get this one 1 over 2 1 over 2 like this. This number 2 will be cancelled out with these 2, so I will get 1 over square root of 2 plus or minus. So I'm going to replace this information into this equation to find b. Okay, equal to 1 over 2a 2 plus or minus. This one is given us, if you simplify, this one is given us plus or minus 1 over square root of 2. Okay, since integral we are talking about a positive number, so I'm going to take only the positive solution. So we'll get square root of I equal to 1 over square root of 2. I'm going to replace a and b with 1 over square root of 2. I will get 1 plus I. Okay, I'm going to simplify this one. All right, I'm going to clean up the board and calculate this integral. Okay, in order to finish off this problem, I'm going to calculate this integral. So I will have a new integral as a g integral, as x goes from minus infinity to plus infinity of e to the minus x squared dx. This one equal the same as minus infinity to plus infinity of minus y squared dy. I'm going to do the product of these two integrals together. I will get g squared equal to, as x goes from minus infinity to plus infinity, and y goes from minus infinity to plus infinity, e to the minus x squared plus y squared dx dy. Okay, so in order to evaluate this double integral, I'm going to use the Jacobian transformation. Okay, what's the Jacobian transformation said? If you have the plane, this plane, for example, from minus a to the a, transfer this one into new plane in terms of theta and r. From this one from 0, we map this one to this one. Okay, I will have transformation from e to the xy to the e r theta in terms of r theta. Okay, so now we have the integral transformation, the double integral over the region D, this region D, of this integral f of xy as a double integral dx dy equal the new integral over the d prime region, which is this one, of the integral of f of xy is multiplied by Jacobian determinant dr d theta. Okay, so I'm going to apply this formula. Okay, let's set x equal to r cosine theta and y equal to r sine theta. Okay, for the Jacobian, we call the determinant, the partial differentiation of x respect to r, the partial differentiation of y respect to r. For the second variable, I will get the partial differentiation of x respect to theta. The fourth one, the partial differentiation of y respect to theta. Okay, so if you calculate this one, the partial differentiation of this one is giving us is given as cosine theta. This one is given as sine theta. This one is given as minus r sine theta. This one is given as r cosine theta. Okay? By calculating the determinant of this one, I will get Jacobian. This one is multiplied by this one minus this one is multiplied by this one, which is r cosine square theta minus with this minus become plus r sine square theta. I'm going to take r as a common factor. I will get r is multiplied by cosine theta plus sine square theta. We know this one equal to 1, which is r. Okay, so now I'm going to evaluate my integral. So for the transformation of this integral, we have this double integral from minus infinity to plus infinity of e to the minus x square plus y square dx dy. So as we said before, transfer this one theta. R it goes from 0 to plus infinity. Theta it goes from 0 to pi. Okay, like this. If you have an open surface, x goes from minus infinity to plus infinity, and y goes from minus infinity to infinity. R is goes from 0 to plus infinity. Okay, R it goes from 0 to plus infinity. For the next one, for theta, theta goes from 0 to pi. Okay, for the, I'm going to replace by doing x square plus y square minus r square. Okay, is multiplied by Jacobian, as we said before, is multiplied by this one, which is r, and dr d theta. Okay, I'm going to clean up the board and breathe this one at the top. In the last board I was working on Jacobian transformation and came up with this results. Now I'm going to calculate, now I'm simply going to calculate this integral. Okay, so I will get g square equal to, as r goes from 0 to plus infinity, I'm going to take r terms outside of this integral because it's not dependent on theta. So we'll get r is multiplied by e to the minus r square of is multiplied by the integral from 0 to pi of d theta. The whole thing is dr. Okay, this one is giving me 2 pi. By taking 2 pi outside of this integral, because it's considered as a constant, I will get 2 pi is multiplied by this integral from, as r goes from 0 to plus infinity, of r is multiplied by e to the minus r square dr. Okay, this one 2 pi. So if you're looking for the primitive of this one, is giving me minus half is multiplied by e to the minus r square. This one is evaluated from 0 to plus infinity. Okay, so with these two will be cancelled out. With this I will get minus pi e to the minus r square. By plugging 0 into this one, I will get minus 1. By switching these two terms, I will get pi is multiplied by 1 minus e to the minus r square. So by r is going to infinity, so r is going towards infinity, I will get, but remember the g, it was from minus infinity to plus infinity to the e to the minus x square dx. Okay, which equal to square root of pi. But remember, this integral was evaluated from minus infinity to plus infinity. Since this function is an even function, so that's mean this integral equal 2 times the integral of, as x goes from 0 to plus infinity. That's mean 0 to plus infinity of integral of minus z square dz equals square root of pi over 2. Okay, Now I'm going to replace this information into the original integral. The original integral, it was I equal from 0 to plus infinity of sine of x squared dx equal the imaginary of I, imaginary of square root of I is multiplied by this integral from 0 to plus infinity of e minus z square dz. We found out imaginary of this number, it was square root of 2 over 2, okay? Because I'm taking only imaginary part, as you see, it was square root of I, it was square root of 2 over 2 plus square root of 2 over 2 is multiplied by I, okay? I'm taking only imaginary number of this one, which is square root of 2 over 2 is multiplied by this value, which we have now, square root of pi over 2. By putting things together, by putting these two together, I will get square root of pi over 8. So the value of this integral equal to square root of pi over 8, okay? So I have done with this problem. Now we have done with this problem. Just consider subscribe. If you have any question or suggestion, just put it in the comment section below. Thank you for watching. I will see you in next video. Bye.